Our next topic is non-ideal solutions. We know that solutions which obey Rolle's law over the entire range of concentration are called ideal solutions. And non-ideal solutions do not obey Rolle's law. For such solutions, delta H mixing will not be equal to 0. Delta V mixing will not be equal to 0. And also the interactive forces on mixing will be different, will be stronger or weaker than those present in the pure components. If the two pure components A and B, A interaction and B interactions will be different from AB interactions. And that is AB interactions can be stronger or weaker than AA and BB interactions. And therefore we have two types of non-ideal solutions. One type of non-ideal solutions, those showing positive deviation from ideal behavior or from Rolle's law, and those showing negative deviation from ideal behavior or from Rolle's law. Now, considering the case of the solutions showing positive deviation from ideal behavior, example for that, a mixture of ethanol and acetone. Now, as you know, in ethanol, the intermolecular force present is hydrogen bond. When acetone is added to this, these hydrogen bonds will break and acetone molecules will get in between ethanol molecules. And the interactive forces between ethanol and acetone is weaker, or those forces are weaker than those present between ethanol or between acetone molecules in pure components. So on mixing, the escaping tendency of acetone and ethanol increases. So more molecules will go to vapor state, and the vapor pressure observed will be more than that given by Rolle's law. And that is, for such a solution, P1, partial pressure of component 1, will be more than that given by Rolle's law. As per Rolle's law, this must be equal to P10 into X1. But here P1 will be observed, vapor pressure will be more than that, partial vapor pressure will be more than that given by Rolle's law. Same way, P2 will be more than P20 into X2. And this means P total, that is P1 plus P2. P total will be more than P10 into X1 plus P20 into X2. So this is called positive deviation. And here the representation, ideal behavior, we know the straight lines show ideal behavior. The observed vapor pressure is more than that given by Rolle's law. So we get curve above those representing ideal behavior. So this is the graph for our representation of a solution showing positive deviation. And for such a solution, delta H, considering delta H mixing and delta V mixing. Now delta H mixing of such a solution, that is enthalpy change during or on mixing. Interactive forces become weaker, and that is the bonds present in pure components break and new bonds are formed. New bonds formed are weaker than the old bonds which were broken, and therefore here energy is absorbed. Overall change on mixing is absorption of energy. So on mixing these two components, a cooling effect will be noticed, and that is the process is endothermic, and hence delta H mixing will be more than 0, or we say delta H mixing of such solution will be positive. And considering the change in the volume, when we mix 10 ml of ethanol with 10 ml of acetone, we expect to get exactly 20 ml of the solution. But we may get 20 point or slightly more volume on mixing these two, because interactive forces are weaker and therefore the molecules move apart, and that causes a slight increase in the volume than the original volume, and hence we say delta V mixing will be positive. So for solutions showing positive deviation, delta H mixing is positive, delta V mixing is positive, and the observed vapor pressure will be more than that given by Rolle's law. Example of such a solution is a mixture of ethanol and acetone. Now coming to the solutions showing negative deviation. For such solutions, when these on mixing, the interactive forces become stronger than the forces present in the pure components. Example, on mixing chloroform with acetone, chloroform CHCl3, acetone CH3COCH3. Now, new bonds, interactive forces will be formed, or bonds will be formed between acetone and chloroform. So here hydrogen bonds will be formed between these two molecules, and this bond formed is stronger than the interactive forces present in pure acetone and in pure chloroform. So escaping tendency of chloroform and acetone in this mixture decreases, and therefore the vapor pressure obtained will be less than that given by Rolle's law. So this is the vapor pressure given by Rolle's law. Now the observed will be less than, so we get a curve below this, and therefore vapor pressure less than that given by Rolle's law. So total vapor pressure also will be less than that given by Rolle's law. This is called negative deviation. And for this, hence delta H mixing will be negative, and that is process will be exothermic. That is because the new bond formed is stronger, so more energy is released than required for breaking the old interactive bonds or forces present, and therefore process is exothermic. On mixing the components, a heating effect can be noticed. Delta V mixing will be negative. Since interactive forces are stronger, molecules come closer, and that causes a slight decrease in the volume of the solution. Example is a solution of chloroform and acetone. And then, so this is about negative deviation and also positive deviation. And now another term, important term comes here is azeotrope. Azeotrope, word meaning is constant boiling mixture. Now this is a binary liquid mixture which on boiling will vaporize, giving vapors of both the components having the same composition as in the liquid state. Now for example, if we have a 95% ethanol and 5% water by mass mixture, 95% ethanol C2H5OH and 5% water mixture. This mixture on boiling, we expect the more volatile component to vaporize faster, and so the vapors should we expect the vapors to be having more of C2H5OH. But on mixing this particular mixture, on boiling this mixture, the vapors we get will have again the same 95% ethanol and 5% water by mass, and that is this binary liquid mixture has same composition in the liquid as well as in the vapor state, and it boils at a constant temperature like a single liquid, and such a mixture is called an azeotrope. So this mixture is an example of an azeotrope. Now azeotropes can be of two types: minimum boiling azeotropes and maximum boiling azeotrope. Now, minimum boiling azeotrope, its meaning is the azeotrope or that binary mixture boils at a temperature which is lower than the boiling points of the pure components. For example, this is an example of a minimum boiling azeotrope. If the mixture is boiling at a lower temperature, that means it produces enough vapors so that the vapor pressure becomes equal to atmospheric pressure, or external pressure at a lower temperature, and that means it has higher vapor pressure. So this means that this must be a solution showing positive deviation. So minimum boiling azeotrophs, these are binary liquid mixtures which show large positive deviation from ideal behavior. Then the second type is maximum boiling azeotrope. Now, maximum boiling, just as in the case of minimum boiling azeotrope, maximum boiling azeotrope is the binary liquid mixture which boils at a temperature which is higher than the boiling points of the constituent liquids. An example is a mixture of 68% HNO3, nitric acid, and 32% water by mass. By mass. So here it is by volume. This is volume percentage and this is mass percentage. So example of a minimum boiling azeotrope, 95% ethanol and 5% water by volume. And maximum boiling azeotrope example, a solution having 68% HNO3 and 32% water by mass. So this is about azeotropes. And the next topic is about vapor pressure of solutions having solids dissolved in liquids.